This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll discuss about hazards and hazard-free relations. So the topics for this class, we will be discussing about the types of hazards like static hazard, dynamic hazard. So first we'll see what do you mean by hazard and why these, what is the effect of hazards in the digital circuits and what are the types of hazards, that is static hazard and dynamic hazard, and if any hazard is there or else is present in a digital circuit, then how to eliminate that hazards in digital circuits, that is elimination of hazards in digital circuits. So now first of all, let us see what do you mean by hazard. So hazards are unwanted switching transient that may appear at the output of the digital circuit. So that means the transients means the change of state, either from 1 to 0 or 0 to 1. If any transients which are unwanted in the output occurs, such type of situations are called as hazards. And such hazards may result in malfunctioning in the output of the circuit. The propagation delay associated with the logic gates in the circuits is a main cause of hazards. So the propagation delay, what do you mean by propagation delay? It is a time taken by the signal to propagate from input to the output. So each and every gate will have its own propagation delay. So this delay leads to this unwanted transients in the output, which are nothing but hazards. So hazards occur in combinational circuits which will cause faulty operation. Faulty operation means, for example, if for any change in the input, the output must be 0. But due to this hazard, the output may change to 1. So that means, and it leads to unwanted output for the given change in the input signals. So that is the hazard which can occur in the combinational circuit will leads to faulty operation. That means it leads to the misfunctioning of the combinational circuit, which is not able to serve its purpose. So next, the hazards can also happen in asynchronous sequential circuits where the logic gates are used. So in a case of asynchronous sequential circuit, along with the flip-flops, we'll also use some extra logic gates. So that circuit, due to that logic gates or else the circuit formed by the logic gates, we may also have hazards in asynchronous sequential circuits also. So which may affect the stable state of the asynchronous sequential circuits. So that means what I want to say is not only in combinational circuits, even in sequential circuit, that is mainly in asynchronous sequential circuit, where we use logic gates along with the flip-flops due to the delays. This also leads to some hazards which may affect the state of the sequential circuit. So there are majorly two types of hazards. The two types of hazards are static and dynamic hazard. So what do you mean by static hazard and dynamic hazard? So let us see the static hazard. When the input to the logic circuit changes, the output has to remain at a particular logic, but instead it may change its value momentarily. That means for some time, actually even if I change the input for a logic circuit, the output has to retain in the same that means the same state. That means output has to be locked at a particular value, that is either at logic 1 or logic 0, but for some time, that is momentarily, the output value may be changing. So such type of hazards are called as static hazards. So if this happens, in the logic circuit, then there exists a static hazard. So even if I change input, the output has to remain at a particular logic value, but it is changing for momentarily. So this type of situation in a logic circuit is known as static hazard. So the static hazards again classified into two types, static 1 hazard and static 0 hazard. So there are again two types of static hazard, static 0 and static 1. What do you mean by static 1 and static 0 hazard? So first of all, let us see static 1 hazard. So instead of remaining at logic 1, the output goes to 0 momentarily. Then the type of hazard that is existing is known as static 1 hazard. So if the output has to remain at logic 1, but due to the change in the input, if the output is changing momentarily to logic 0, such type of hazard is known as static 1 hazard. Let me explain that with diagram, that is timing waveform. So here this is the waveform here. So actually the output is 1, but due to the change in the input, it has to remain in 1 itself. The output has to remain at a logic 1, but momentarily it is changing to 0 and again it is going back to 1. So such type of hazard is known as static 1 hazard. Actually the output should remain at logic 1 even for the change in the input, but it is changing to logic 0 momentarily. So such type of hazard is called as static 1. Next, static 0. Static 0, I hope you can define static 0. So instead of remaining at logic 0, so if the output momentarily goes to logic 1, instead of remaining at logic 0, then there exists again a hazard, and that type of hazard is called as static 0 hazard. So output has to remain at logic 0, but due to the change in the input, momentarily it is going to 1 and again it is coming back to 0. Then such type of hazard is known as static 0 hazard. So this is the timing diagram which is explaining the static 0 hazard. Actually the output is 0, but due to the change in the input, it has to again remain at logic 0, but for some time or else momentarily, it is going to logic 1 and again coming back to logic 0. Such type of hazard is known as static 0 hazard. So that is about static hazard. Static hazards are two types, static 1 and static 0. So now coming to the dynamic hazard. So a hazard is said to be dynamic if the output changes 2 or more times when it should change from 1 to 0 or 0 to 1. So that means if the output has to change from 1 to 0 or 0 to 1, then instead of changing only once, if the output changes more than once, then there exists an hazard which is called as dynamic hazard. So instead of changing only one time, it is changing more than one time or else 2 or more times. So then that type of hazard is known as dynamic hazard. This is the waveform that we can explain the dynamic hazard clearly. So here the output is 1, but it has to go to 0. But it is not going for 0 only once. It is going to 0 and 1 more than once. So that is why this type of hazard is known as dynamic hazard. That means when the input changed only one time, but the output change in the output is happening more than one times, then that type of hazard is called as dynamic hazard. Now coming to the illustration of static hazard, how to find out the hazards in a logic circuit, how to find whether there is a hazard or not. So that is illustration of static hazard. So in order to explain this, I just want to consider a logic circuit. So this is a logic circuit where we have one inverter, 2 OR gates and 1 AND gate. So let us consider this logic circuit in order to explain how to detect whether there is a hazard or not. So now let us see. First, let us assume that the 3 inputs of logic circuit, initially I am assuming that the 3 inputs of the logic circuit are 0. I am considering that initially the 3 inputs of the logic circuit are 0. Then in that case, the output of this inverter is 1. So as these are the OR gates here, the output of the first OR gate, which is nothing but D becomes 1. Whereas the output of the second OR gate, which is equal to both the inputs are 0. So this is 0. And hence the function, and these outputs of these 2 AND gates are given to the AND gate. OR gates are given to the AND gate. So the function output will be 0. So that means let us assume that 3 inputs of the logic circuit, A is equals to B is equals to 0. This input will cause the output of OR gate 1 to be D is equals to 1, whereas the output of second OR gate 2 to be E is equals to 0, and hence the output of the logic circuit F is equals to 0. Now, so here now I want to detect whether there is a hazard or not. So for that, what I am doing, so for, now I'm considering that the input B now it changes from 0 to 1. So now the input changes from 0 to 1. Initially all the inputs were 0. Now what I am doing, I am just considering that input is B has changed from 0 to 1. Now let us analyze the output of this all these gates. So here it will cause the output of OR gate, output of OR gate 1. So as it is 1 now, so it becomes 0, and this is also 0. Only B is changing from 0 to 1. A and C are remaining 0. So this output of this OR gate 1 is 0, whereas the output of OR gate 2 is also 0. So and hence the function output, the total output of the logic circuit should be 0. But what is happening? So while the input changes from 0 to 1, that is the input B changes from 0 to 1, the delay in the output of NOT gate and OR gate 1 is more than the delay in the OR gate 2. Why? Because so the output of the output of the OR gate has to wait for the input which has to come from the NOT gate. So because B is first applied to the NOT gate, so every gate will have its own propagation delay. So in order to get its complement, the inverter will take some time. So that means here the delay of this OR gate is nothing but the delay of the inputs to propagate, and also we have to wait for this OR gate has to wait for the output of the NOT gate. So that is how. So whereas we don't have any other gates here in the second OR gate input circuit. So that is why the OR gate is 2 delay is less than the OR gate 1, because as the OR gate 1 has to wait for the output of inverter, so the delay of OR gate 1 is more than the delay of OR gate 2. So due to the lesser delay, the output of gate 1, the output of gate 2 changes to 1. So actually what is the input here? A is 0, but B is now changing from 0 to 1. So it is 1 now, it is 0. So now what happens? E becomes 1 now. So initially it was 0. Now due to the change in the input B from 0 to 1, so before the output of OR gate 1 is arrived, the output of the OR gate 2 changes to 1, and hence what happens, as it is 0, initially it was 0, now the output of this gate is 1, so both are 1, so it remains 0. It remains 0. So here, while the input changes from 0 to 1, the delay in the output due to NOT gate and OR gate, NOT gate and OR gate is 1. OR gate 1 is more than the delay due to the OR gate 2. Due to the lesser delay, the output of gate 2 changes to 1 before the output of gate 1 changes to 0. Okay, so initially it was 1. So because when both are zeros, that is 1. So initially it was 0. Actually it has to change to 0 now. But what happens? Before it changes to 0, the E output will be changing to 1. So that is how. So at this particular time, both the outputs of the gate 1 and 2 will be momentarily equal to 1. Momentarily equal to 1. Thus, the output of the logic circuit will be 1 for a short period of time. In this way, there exists a static 0. So actually, let me explain once again. So here, initially what we are doing, we are taking initially the inputs are 0, 0, 0. So initially 0, 0, 0. So here it is coming 1. So D is equals to 1. Whereas 0 is coming here. E is equals to 0. And hence the function output is 0. Now let us consider what is happening here. Now the input B is changing from 0 to 1. Input B is changing from 0 to 1. So as we have delay of this NOT gate. So before changing so it has to change to 0. It has to change to 0 because B has become 1 now. So the output of inverter becomes 0. So then it has to become 0 now. So what happens due to the delay of the circuit, that is of the OR gate 1 is greater than the delay of the OR gate 2, and hence before the output of OR gate 1 changes, OR gate 2 output changes here, and that becomes here, as this is 1 now, so this changes to 1. This changes to 1 here. So as both are 1s, so now what happens? For some time it will become 1 now. So actually when the V changes from 0 to 1, the output of the OR gate also should change to 0. But due to the delay of OR gate 1, which is greater than the delay of OR gate 2, so before the D changes to 0, as E changes to 1, so momentarily the output becomes 1. Momentarily the output becomes 1 here. So that is why here, as both are 1s here, the output becomes 1, but it should stay in 0. So that is why we are calling that there is a static 0 hazard present in this circuit. Why? Because even though the input has changed to 1, B has changed to 1, the output of the AND gate should be 0. But momentarily what happens? Due to the delay of OR gate 1 greater than delay of OR gate 2, so before the D output changes to 0, E output changes to 1, and hence for that instant of time, the function output is becoming 1. Instead of remaining at logic 0, the output is changing to logic 1. So that is how we can say that there exists a static 0 hazard. So this is how we can detect the hazards here. Okay, so now I want to explain these hazards in graphical way, that is using the waveforms here. Now let us consider A is equals to 0, B is equals to 0, initially C is equals to 0. When A 0, B 0, C 0, what should be the output of D? The output of D, so this is the circuit, right? So when A 0, B 0, the output of D, that is a OR gate 1, becomes 1. So that is why, so here the output of D is 1 initially. Now E is 0 because the circuit is like this, right? So this is the OR gate. So where we have an inverter, okay. So this is A, B, and this is one more OR gate where we have BC. So this is B and this is C, and we have an AND gate. We have an AND gate, okay, F. So now what is happening here? When this is C, so this is D, E, right? So now when A 0, B 0, C 0, so the output is 0, whereas E output is also 0. So this is 1. This is 1, E output is 0. So D output is 1 and E output is 0. So as this is equals to AND of 1 and 0 is 0. F is 0. Now, as here at this moment, B is changing from 0 to 1. This is changing from 0 to 1. So due to the gate delay, so what is happening? The output is not changing instantaneously because of delay of OR gate 1 greater than the delay of OR gate 2. So that is why it remains 1. But actually it has to become 0. So it remains 1. Whereas E is remaining 0 when it is changing, because gate delay is there, right? So this is the delay of gate 1. Only one gate is there. So this is the delay. The delay of OR gate 2 is less than the delay of OR gate 1. So that is why after the delay, it is changing its state to 1 because the input has been changed to 1. So 0 plus 1 is 1. So after the delay, it is changing. Actually, it has to change here, but due to the delay, it is changing bit later. It is changing bit later, but the delay of this first OR gate is greater than this one. It is changing after that. So because this is a, let us consider this as the NOT gate delay and this as the delay of OR gate delay. Two gate delays we have. Okay, whereas this is only OR gate delay. So that is why it is not changing its state to 0, whereas this is changing 0. So where both the inputs to the AND gate are becoming 1 and hence the output F is becoming 1 for this time period. But it is not required here. But it is not required here. And this is happening due to the gate delay. And that is why this is called as static 0. Actually, it should remain at 0 even if the input changes from 0 to 1. So after these 2 delays, now what is happening? The D output is changing from 1 to 0. So now this is 1, this E output is 1 and this one is 0. So 1 into 0 is 0. So this is the explanation of hazard with respect to the waveform. So that means that is how we can detect a hazard, whether it is present or not, and if it is present, what kind of hazard it is. So as the output has to remain 0 even if B is equals to 1, but it is going to 1 for momentarily and again coming back to 0. So the type of hazard here, it is static 1 hazard. Okay, static 0 hazard. It has to maintain 0, but it is going to 1 momentarily. So that is why we are calling it as static 0 hazard. Right? So now we have detected a hazard is there in that circuit. Now how to eliminate that hazard? So if a hazard exists in a circuit, it is to be eliminated to produce an error-free output. Right? Actually, I don't want my output to go to logic 1. It has to be in logic 0. I should eliminate that error. So we for discussing this elimination of hazard, I'm just considering a Boolean function, that is AB bar plus BC. Just now we have seen the logic circuit for this expression. So I'm considering this expression. Now I want to eliminate the hazard present in this logic circuit, right? So for that, how can we eliminate the hazard? So a K-map can be implemented for the given expression from which the logic circuit is drawn. Okay, so here we have the expression. So first we have to draw the K-map. So in order to draw the K-map, what should we remember? It should be in canonical form. Okay, canonical form means it should be in standard form, that is a sum of products form or else product of sums form. Okay, so it should have all the minterms, all the variables. Each term should have all the variables of the given function. Actually, how many variable Boolean function it is? 3 variable function. But each term is having only 2 variables. So for drawing the K-map, first I have to convert it into standard form. So first I am taking the Boolean function. What is the Boolean function given here? F is equals to AB bar plus BC. So what is the variable missing in the first term? C is missing. So I want to multiply this one with C plus C bar. And in the second term, A is missing. So A plus A bar into BC. So if I write this one, A B bar C plus A B bar C bar plus A B C plus A bar BC, right? So what this represent? This represent 1 0 0 1 0 1, and this is 1 0 0 1 1 1, and this one is 0 1 1. So that is, this is minterm 5. So I can write this one as summation m of 5 or else 3 4 5 7. 3 4 5 7. 3 4 5 7. Now I am mapping this one with the K-map here. So this is a K-map. So how many variable function it is? It is a 3 variable K function. So that is why I am taking a 3 variable K-map. So A, B, C are the 3 variables I am considering. So this is 0, 1, 3, 2, 4, 5, 7, 6. So what is the minterms that are included here? 3, 4, 5, 7. 3, 4, 5, 7. Right? So just I am grouping. So I will be getting this expression. Right? So if I group this one, what is the expression I will get? A. Okay. A. This is A. And this one is B bar. A, B bar. And this is BC. Right? So this is the mapping of Boolean function. So what we are doing, I want to eliminate the hazard here. How to eliminate the hazard? First we need to draw the K-map. So first for the given function, which is to be drawn in the logic, implemented using logic gates, I want to implement it using K-map here. This is the K-map, and now this is the logic circuit. So the logic circuit here is having one inverter, one AND gate, 2 AND gates, and 1 OR gate, right? So here, if you look at this logic circuit, so what we can observe, we have 1 AND gate, 2 AND gates, and 1 OR gate. So if you observe here, the one of the input is this AND gate. Okay, this AND gate is coming from the inverter. So here now, that means if you observe, whereas we don't have any other logic gates at the input side of second AND gate. So that is what we can understand here is the delay of gate 1 is more than the delay of gate 2. Okay, so if a delay of two gates are not equal, definitely there exists hazard. Which we have which we understood from the previous circuit diagram and explanation. So now what I should do? I want to eliminate this hazard. So to eliminate that hazard, we need to check the K-map, and in that K-map, the hazard can be detected in a digital logic circuit. In the K-map, if two adjacent ones are not enclosed, then there exists a hazard. So now let us try to look at the K-map here. So here we have formed the two pairs, but here even though these two are adjacent, they are not enclosed. So this leads to a hazard. So that is one way to find out the hazard. This is another way. How can we detect the hazard? So just draw the K-map and you need to identify if any two groups are not enclosed, which are adjacent to each other, then this leads to a hazard. Either it may be a static 1 hazard or static 0 hazard. As these are said to be adjacent to each other, but they are not enclosed here, this leads to a hazard. Okay, now how to eliminate this? So in order to eliminate this, what we want to do, to eliminate the hazard, those minterms must be enclosed by introducing another minterm as shown below. So now what we are doing, in order to eliminate that hazard which leads to the malfunctioning of the circuit, so what we need to do, even though it is not required, we should enclose those two minterms together such that another term is going to be included in the given Boolean function. So now what we are doing, actually the two groups are formed here, but as these two are also adjacent to each other, so I am also forming another group such that the hazard is eliminated. This is the procedure for eliminating hazard. So now what is a term that is prime implicant representing this one? Actually this was A B bar, whereas this was B C, whereas for this one A C. Okay, an extra term we are adding is AC. So now the hazard free circuit is this one. So that is AB bar. Okay, this one is BC and this one is AC. So this is the hazard free circuit. So what we are doing, we are identifying the hazard, whether there exists a hazard or not, by implementing the function in the K-map. So how we can identify the hazard? So if two cells are said to be adjacent but they are not enclosed together, then that leads to a hazard. Now how to eliminate that? So we just want to eliminate that hazard by adding an extra term, by enclosing the two minterms which are adjacent to each other. Even if it is not needed, in order to eliminate the hazard, we are grouping them together such that an extra term is added. Okay, so this is the hazard free circuit. Now let us see what happens initially. This is 0 0 0. Let us consider. So it is 1. So these are 0 0. This is also 0 0. So now what is the output of this first AND gate? AND gate is 1 and this AND gate is also 1 and this AND gate is, this is 0. This is 0. So the output becomes 1. So this is first output. Now if I change this input to 1, if I change this input to 1 here, so now what happens? This becomes 0 now. If this becomes 0, so this becomes 0 and this is already okay, BC. So now it is already only one of the input becoming 1. So this is also 0, whereas AC, so AC is also 0. Because these are the AND gates, right? So if any one of the input to the AND gate is 0. So what happens? Here, even though the input has changed from 1 to 0, the function output is remaining as 1 because this is an OR gate. an OR gate. So that is how we are eliminating the hazard here. So if you look at the previous circuit, what was the previous circuit? A, B bar. So A, B bar. So this is, this is A, B bar, A, B and B, C. Okay, B, C. So this was the function. So now let us consider 0, 0, 0. So now what is happening? The output of this AND gate becomes 0, whereas this output of this AND gate is also 0. Whereas this output of this AND gate is also 0 here. So actually, sorry for the wrong interpretation. So actually, so when all the inputs are zeros, so what is happening here? This is becoming 1. As this is an AND gate, so the output of this AND gate is 0, whereas this is also 0, this is also 0. Now if I change my input to 1, so this becomes 0 here. Again, this output is also 0, this is also 0 and this is also 0. So function output in both the cases is 0. Okay, so that means we don't have any type of hazard. So now for example, if I consider 0, 0 here, so the output of this AND gate is 0, this AND gate is 0 and the function output is also equal to 0. Whereas if I change my input this to 1, so now this is 0, again this is 0 and this is 0. So if I change this input to 1, let us consider. If I change this input to 1, so here this is 0 anyhow. So as it is 1, the output becomes 1. Output becomes 1. Whereas this is 0 again. So actually as this is 1, actually it has to change to 1 here. But it is remaining 0. It is remaining 0 where it has to go back to 1. So that means here there exists a static 1 error where it is going to be eliminated by using this circuit. So that is how you can eliminate the hazards. Okay. So now let us consider another example. Construct a hazard-free logic circuit for a Boolean function. So you may get some questions like eliminate the hazards in a given logic circuit. First we need to identify the hazard and then we need to eliminate the hazard. So here the given Boolean function is as a summation m of 0, 2, 6, 7, 8, 10, 12. So this is a Boolean function. Now what I want to do? I want to implement this one. I want to eliminate the hazard. First of all, I want to detect the hazard. And if there is any error, just I want to eliminate it. So for that, what we need to do? In order to detect the hazard, first we need to implement the Boolean function in a K-map. So this is a K-map. How many variable K is required? 4 variable K-map. So it is a 4 variable K-map. 0, 2, 6, 7 and then 10, 8, 10 and 12. So these are the cells marked with 1 for which the function output is considered to be 1. So now I can form a quad with all these corner cells, whereas I can form a pair with this and I can form a pair with this. Okay, now all the ones have been covered. So actually, if you could see, these two are said to be adjacent, but these are not enclosed. So this leads to a hazard. So that means here, what are the terms we have got here? This one can be represented as A and this is B, A, C bar, D bar. Whereas this one, this quad is represented with B bar and this is D bar, B bar, D bar. Whereas this pair is nothing but A bar, B, A bar, B, C, A bar, B, C. So this is the Boolean function, right? So now we have identified that there is a hazard because these two cells are said to be adjacent, but these are not enclosed together, which leads to a hazard. Now how to eliminate that? So what we need to do? We need to add an extra term in the Boolean function by enclosing that two terms together. Okay, now to eliminate the hazard, the min terms A bar B C is enclosed with the near min term by grouping as shown. So this is an extra group formed which is not needed, and this group is formed in order to eliminate the hazard. And due to this, what term is going to be added here? This pair is formed by these two rows and this column, right? So for these two rows, A value is same, which is 0. So A bar, whereas C value and D value are also common, whereas C is 1, D is 0, D complement. So that means I want to add one extra term such that these two ones which are adjacent to each other are also enclosed together in order to eliminate the hazard. So this extra term is going to be added in the Boolean expression, and now the modified Boolean expression is this one: B bar D bar plus B A bar B C plus A C bar D bar plus A bar C T bar. So this is a Boolean expression. So now I can implement that Boolean expression. So this is our hazard-free Boolean function. So even though an extra logic gate is added, but what is the advantage here? We are going to eliminate the unwanted transients between the output for the respective changes in the input. So this is why we are eliminating. What is the importance here? In order to avoid the malfunctioning of the circuit, we need to eliminate the hazard. So even though the circuit becomes complex, but it gives the proper output, or else the functionality of the circuit is maintained as specified, and hence we need to eliminate the hazard even by adding extra logic gates. So this is the implementation of the hazard-free circuit. Okay, so this is the logic circuit which has been in which we have eliminated the hazard. So this is about hazards. So in this lecture we have discussed about hazards, the various types of hazards, how to detect the hazard and how to eliminate the hazard. So with an example I have discussed about hazards and hazard-free relation. So I hope it is clear to you all. That's all for this lecture. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.